Most parents buy 3D printers thinking they're getting an educational tool. What they actually get is a $300 desk ornament that fails halfway through the first science fair project and teaches their kid nothing except frustration. The printers that actually build employable skills look completely different from the ones marketed to families. I'm Rajiv Patel, and I've spent the last 8 years watching which machines produce students who walk into engineering internships with real capabilities versus which ones just print baby Yodas.
You're listening to the STEM Lab podcast. Quick thing up front. Everything you're about to hear, the research, the technical evaluation, the recommendations, all of that comes from real authors with actual domain expertise. The voice delivering it is AI generated, but the content itself is completely human-written and verified. Just wanted to be transparent about that from the start. If you've been listening to the show for a while, thank you. Honestly, knowing people are getting value from this keeps the whole operation running. And if you just found us, glad you're here. We focus on STEM learning tools that build employable skills, not just toys that end up in a closet after 2 weeks. New episodes drop every Monday, Wednesday, and Friday. Let's jump into today's topic.
The best printers for kids and teens differ from consumer models in 3 critical ways. They require minimal troubleshooting that derails learning momentum, they map to industry-standard CAD workflows without artificial simplification, and they survive the repeat failures inherent to skill acquisition. This entire discussion focuses on machines that build employable competencies, not desk ornaments. So what actually is a 3D printer for educational use? At the technical level, it translates digital models into physical objects by depositing thermoplastic filament layer by layer. Educational models prioritize reliability over feature density, and that distinction matters when a failed print at 11 p.m. the night before a science fair submission can't be rescued by tech support. The fundamental technology is FDM, which stands for Fused Deposition Modeling. It's identical to what's used in automotive prototyping and aerospace R&D. Entry-level printers use the same core process as industrial Stratasys machines, just with smaller build volumes and consumer-grade components. That technical continuity is the entire value proposition. A teen who masters G-code troubleshooting, bed leveling, and slicer optimization on an entry-level printer walks into their first engineering internship with skills that translate directly to $40,000 industrial systems. Educational printers fall into 2 camps. Enclosed systems with proprietary ecosystems trade flexibility for consistency. Open-frame machines expose the full mechanical complexity. The latter frustrates beginners but teaches root cause analysis, which is a higher value skill in the 2026 hiring market than clicking print on a black box. Here's what matters. The learning objective isn't the printed object, it's the iterative problem-solving cycle. Model in CAD, slice with path optimization, diagnose layer adhesion failures, adjust parameters, repeat. That loop mirrors actual product development workflows at companies currently hiring mechanical engineers and industrial designers. Now let's talk about how the technology actually works for young learners. An FDM printer requires 3 skill domains that map to distinct career competencies: CAD modeling, which builds spatial reasoning and parametric design skills; slicing software configuration, which teaches applied physics and quality cost trade-offs; and mechanical troubleshooting, which develops root cause analysis under ambiguous failure modes. Starting with the CAD to physical workflow. Students design in either Tinkercad, which is browser-based with limited parametric capabilities but zero install friction, or Fusion 360, which is industry standard with full parametric history and a steeper learning curve, but directly applicable to mechanical engineering roles. Both export STL files, a mesh format that represents surfaces as triangulated polygons. That mesh then imports into slicing software like Cura, Prusa Slicer, or proprietary alternatives. The slicer converts 3D geometry into G-code, which is machine instructions specifying nozzle path, extrusion rate, temperature, and movement speed for each layer. A typical 4-hour print generates 50,000 plus lines of G-code. Students don't write it manually, but understanding the relationship between slicer parameters and resulting G-code teaches the optimization trade-offs that define manufacturing engineering: strength versus material cost, speed versus surface quality, complexity versus failure risk. Moving on to mechanical operation and failure modes. The print head, called a hot end, melts filament to approximately 200 degrees Celsius for PLA, 240 for PETG, 250 for ABS. Material extrudes through a 0.4 millimeter brass nozzle while moving in X and Y coordinates. The bed lowers incrementally along the Z-axis after each layer. First layer adhesion determines print success more than any other variable. It requires bed leveling accurate to 0.05 millimeters across the entire surface. This is where educational value separates from entertainment value. Cheap enclosed printers auto-level and hide the process. Better learning happens when students manually adjust bed springs with a feeler gauge, building tactile intuition for mechanical tolerances that apply equally to gearbox assembly or PCB mounting hardware. Common failure modes include warping, which is differential thermal contraction causing corners to lift, stringing, which is excess plastic deposited during non-printing moves, layer delamination from insufficient interlayer bonding due to temperature miscalibration, and clogging, where heat creep causes filament to expand and jam inside the hot end. Each failure mode has 4 to 6 potential root causes. Diagnosing them requires hypothesis generation, controlled variable testing, and documentation. It's the scientific method applied to hardware debugging. Now let's get into slicer configuration as applied physics. Layer height trades resolution for speed. 0.12 millimeter layers produce smooth surfaces but take 3 times longer than 0.28 millimeter layers. Infill density affects structural strength and material cost. 20% honeycomb infill uses half the filament of 40%, but reduces compressive strength by approximately 60%. Print speed impacts cooling time. Pushing a Creality ender above 60 millimeters per second on detailed geometry causes insufficient solidification before the next layer deposits. Students who engage with these trade-offs learn engineering constraint optimization more effectively than any textbook problem set. They're making real decisions with immediate physical feedback, iterating on designs with material and time costs they feel personally. So why does this technology actually matter for skill development? The 2026 hiring landscape prioritizes hands-on prototyping ability over theoretical knowledge. Engineering managers at firms I consult with consistently report that entry-level candidates lack practical troubleshooting skills. They can calculate stress concentrations, but can't diagnose why a physical part failed during testing. Here are the employable competencies developed. A teen who runs 50-plus prints across 6 months acquires CAD proficiency. Fusion 360 skills listed on a resume signal readiness for mechanical design roles. I've watched hiring managers move candidates from maybe to interview piles based solely on portfolio projects showing parametric modeling competency. They develop manufacturing constraint awareness, understanding that a 45-degree overhang requires support material, adding cost and post-processing time, while a 30-degree overhang doesn't. That's the foundation of design for manufacturability, a $15,000 to $20,000 salary differentiator in mechanical engineering roles. They learn systematic debugging, the process of isolating whether a failed print stems from bed adhesion, temperature calibration, filament moisture content, or slicer settings mirrors software debugging, circuit troubleshooting, and experimental design across all technical disciplines. And they gain material science fundamentals, experiencing how PLA becomes brittle below 10 degrees Celsius, how PETG resists UV degradation better than ABS, how layer orientation affects tensile strength. These aren't abstract concepts when you've personally broken test specimens and correlated failure modes to material properties. There's also integration with robotics and electronics projects. 3D printing transforms from isolated activity to enabling infrastructure when combined with Arduino robotics kits or AI learning projects. Students design custom sensor mounts, prototype chassis modifications, create enclosures for circuit boards, bridging digital and physical domains in ways that mirror actual product development cycles. I've run my own children through this exact progression. Block-based coding with screen-free robotics, transition to Scratch and Python, then CAD and 3D printing to manufacture custom parts for their robots. That integrated skill stack, software plus electronics plus mechanical design, is what distinguishes candidates who get summer internship offers from those who don't.
Let's talk about types and variations, specifically architectural differences that affect learning outcomes, starting with enclosed versus open frame designs. Enclosed printers maintain stable thermal environments, reducing warping and enabling ABS printing without room temperature sensitivity. They're safer, no exposed hot components, but hide mechanical complexity. Students learn operation, but not maintenance or modification. Open frame designs expose all mechanical systems: belt tension, lead screw alignment, stepper motor operation, cooling fan placement. Every component is visible and user serviceable. This transparency has pedagogical value, but requires parental acceptance that learning includes failed prints and troubleshooting sessions. Next, Cartesian versus Core XY motion systems. Most educational printers use Cartesian kinematics, independent motors for X, Y, and Z axes. Simple to understand, straightforward to troubleshoot, directly maps to CNC milling and laser cutting systems students encounter later. Core XY designs use two motors working in tandem to control X and Y movement. Faster acceleration, better high-speed performance, reduced moving mass, but adds kinematic complexity that offers limited educational value for beginners. Then there's proprietary versus open-source ecosystems. Proprietary systems lock students into manufacturer filament, cloud slicing software, and walled garden model repositories. They reduce troubleshooting burden but cap skill development at operational proficiency. Open-source printers running Marlin firmware accept any filament, work with Cura, Prusa Slicer, and Simplify 3D, and expose configuration files for direct editing. Students graduate from using a product to understanding a system, the difference between a video game player and a game engine developer. Now let's get into key selection criteria, lab specs, and capability milestones, starting with technical compatibility requirements. Operating system support varies dramatically. Browser-based slicers work across Windows, Mac OS, and Linux, but sacrifice advanced features. Desktop slicers offer full control, but Prusa Slicer requires Windows 10 Plus or Mac OS 11 Plus, while Cura runs on older systems, including Linux distributions. Connectivity options determine workflow friction. SD card transfer is universal but tedious. USB direct connection is occasionally unstable. Networked printing requires static IP configuration and router access. Some models offer Wi-Fi with mobile app control, reducing friction but adding cloud dependency. Fine for home use, problematic for school networks with content filtering. Firmware ecosystem matters for expandability. Marlin-based printers accept community-developed improvements like linear advance, pressure advance, and input shaping. Proprietary firmware limits students to manufacturer-approved features.
Moving to build volume and material compatibility. Build volume determines project scope. The standard 220 by 220 by 250 millimeter envelope handles 90% of educational projects. Larger volumes enable architectural models and multi-part assemblies, but increase footprint and cost. Filament compatibility gates material science exploration. PLA-only machines simplify operation, but prevent students from experiencing mechanical property differences across materials. PETG capability adds chemical resistance and layer adhesion strength.
ABS enables acetone vapor smoothing and high-temperature applications, but requires enclosed build chambers. Let's talk about power requirements and safety infrastructure. Most desktop printers draw 150 to 250 watts during printing, similar to a desktop computer. They require grounded 120-volt AC outlets and should not share circuits with space heaters or power tools. Thermal safety features vary substantially. Quality printers include thermal runaway protection, where firmware monitors temperature sensors and shuts down if readings exceed safe ranges, and auto shutoff on print completion. Cheaper units lack these protections, which is a legitimate fire risk when left unattended. Ventilation requirements depend on materials. PLA emits minimal VOCs. ABS and PETG require exhaust ventilation or activated carbon filtration. Now, durability and maintenance expectations. MTBF, or mean time between failures, isn't published for educational printers, but observational data from school deployments suggest cheap printers under $250 expect component replacement every 200 to 300 hours. Mid-tier printers in the $300 to $600 range, 500 to 800 hours between major maintenance. Premium printers over $600, 1,000+ hours, but still require regular consumable replacement like nozzles, build surfaces, and belts. User-serviceable design determines whether maintenance teaches or frustrates. Printers requiring hex keys and published assembly diagrams enable student-performed repairs. Models with glued components or security screws force reliance on manufacturer service, which is pedagogically worthless. Let me walk through a product evaluation framework, matching machines to skill progression. Starting with elementary school entry point, ages 8 to 11, the primary objective is build confidence through successful prints while introducing CAD basics. Technical requirements include enclosed design with automatic bed leveling, print resume capability for power failure recovery, PLA-only compatibility is acceptable at this stage, maximum 2-step startup process, and visual or audio status indicators. Skill milestones? By 50 hours of use, students should independently import STL files, adjust scale and orientation, initiate prints, remove completed parts without damage, and identify when support material is required.
One printer that fits this profile has one significant limitation: proprietary filament cartridges that cost approximately 40% more than commodity spools. That premium buys reliability. Students in this age range can't troubleshoot extrusion problems during a print. Moving to middle school development, ages 12 to 14, primary objective is transition from operator to engineer, understanding why settings matter, not just which buttons to press. Technical requirements include open or enclosed acceptable, though open frame is preferred for mechanical visibility. Manual bed leveling capability to build troubleshooting skills, multi-material support, PLA and PETG minimum, direct drive or Bowden tube, both teach relevant principles, and it requires desktop slicer with exposed parameters. Skill milestones? By 100 hours of use, students should create original CAD designs in Tinkercad or Fusion 360, optimize slicer settings for specific geometries, diagnose and correct first-layer adhesion failures, measure dimensional accuracy and iterate designs, and calculate material costs for projects. One specific model occupies the sweet spot here. It's mechanically simple enough for students to fully comprehend, frustrating enough to require actual problem solving, and costs little enough that modification and experimentation carries low risk. The build volume handles science fair projects without spatial constraints. The specific flaw is bed leveling, requires patience and repeated adjustment. Springs lose tension after thermal cycling. Some students find this tedious. I consider it essential skill building for mechanical tolerance awareness. Now, high school advancement, ages 15 to 18. Primary objective is match or exceed capabilities of college makerspace equipment, enabling portfolio-quality work for university applications. Technical requirements include direct drive extruder for better flexible filament handling,
input shaping or pressure advance firmware for higher speed without quality loss, networked operation with remote monitoring, build volume 250 millimeters plus to enable multi-part assemblies, and compatibility with engineering-grade materials like nylon and carbon fiber composites. Skill milestones? By 200 hours of use, students should design parts with manufacturing constraints in mind, things like draft angles, wall thickness, tolerance allocation. Select materials based on mechanical requirements, modify firmware parameters for custom materials, design and print functional mechanical assemblies like gears, linkages, and enclosures, and document projects with CAD and CAM workflow suitable for portfolio submission. One high-end option delivers professional-grade output with minimal tuning. Core XY Motion enables 250 mm per second print speeds without quality degradation. The enclosed chamber handles ADS and ASA without warping. Multicolor capability isn't pedagogically critical, but enables complex projects.
The flaw is it's almost too reliable. Students can operate it successfully without learning the underlying mechanical principles that open frame printers force them to confront. For pure output quality, it's excellent. For maximizing learning per hour, other models offer comparable performance with more transparent system architecture. Let's talk about progressive learning path integration. 3D printing capability doesn't exist in isolation. It's infrastructure for broader STEM skill development. Month 1 to 2 is operational proficiency. Print pre-made models from Thingiverse or printables. Learn slicer basics like supports, orientation, and scale. Build intuition for print time versus quality trade-offs. Establish maintenance routine for bed cleaning and filament storage. Month 3 to 4 is CAD fundamentals. Complete Tinkercad tutorials, approximately 8 hours. Design simple geometric objects like boxes, cylinders, nameplates. Learn Boolean operations, union, difference, intersection. Iterate on designs based on printed results. Month 5 to 6 is applied problem solving. Design custom parts for existing projects like robotics, electronics, science experiments. Measure existing objects and create replacement parts. Learn calipers usage and dimensional accuracy verification. Document design decisions and iteration cycle. This phase integrates with robotics projects and renewable energy experiments. Students design turbine blades, sensor mounts, gear trains, and structural components. Month 7 to 12 is advanced manufacturing concepts. Multi-part assemblies with mechanical constraints like clearances, press fits, snap fits. Material selection based on mechanical requirements. Cost optimization through topology optimization and infill strategies. Fusion 360 progression, including parametric modeling, simulation, and generative design. Students operating at this level produce portfolio quality work suitable for university applications and internship discussions. They understand manufacturing constraints that most mechanical engineering undergraduates don't encounter until junior year. Now, infrastructure requirements, setting up for sustained success. Starting with physical space allocation. Minimum 4 by 3 foot workspace accommodates printer, filament storage, toolkit, and post-processing area. Printers vibrate during operation. Place on solid tables, not particle board or lightweight desks that amplify noise. Dedicated circuits prevent tripped breakers during long prints. I've lost 18-hour prints to power interruptions from unrelated appliances on the same circuit. Essential accessories and consumables. Filament storage matters because PLA and PETG absorb moisture from air, degrading print quality. Store in sealed containers with desiccant packs. Budget $20 to $30 for airtight bins.
Toolkit includes flush cutters for removing support material, needle files for cleaning holes, calipers for dimensional verification, hex key set for assembly and maintenance, and scraper for part removal. Total cost approximately $40 to $60. Replacement parts inventory. Extra nozzles because brass wears out, $15 for a 10-pack. Spare PTFE tubing, $10. Replacement build surface, $20 to $40 depending on type.
Budget $50 to $80 for initial inventory. Safety protocols and risk mitigation. Thermal hazards first. Nozzles reach 250 degrees Celsius. Beds reach 100 degrees. Establish no-touch rules during and immediately after printing. Silicone finger guards, about $8, prevent burns during part removal. Ventilation. Even PLA emits ultrafine particles during printing. Run HEPA air purifiers or print near open windows. For ABS, use activated carbon filters or exhaust fans venting outdoors. Fire risk. Thermal runaway is rare but catastrophic. Never leave budget printers unattended. Install smoke detectors near printing area. Consider remote monitoring cameras for visibility during unsupervised hours. Let's talk cost analysis and ROI on educational investment. Initial capital outlay breaks down like this. Budget tier, $200 to $350, sufficient for skill development through middle school. Mid-range, $350 to $700, supports high school projects and portfolio work. Premium, $700 to $1,200, matches college makerspace capabilities, suitable for serious pre-engineering students. Ongoing operational costs. Filament consumption. PLA costs approximately $18 to $22 per kilogram. Typical science fair project uses 100 to 300 grams, that's $2 to $6. Budget $15 to $30 per month for active users. Electricity. 200-hour print time per month at 200 watts average equals 40 kilowatt hours, which is $5 to $6 at national average rates. Replacement parts. Budget $50 to $100 per year for consumables like nozzles, build surfaces, and belts. Comparative value versus alternatives. Makerspace memberships run $60 to $120 per month in most metro areas. A $400 printer pays for itself in 4 to 7 months of use, while delivering on-demand access that doesn't require transportation or schedule coordination. Educational application benefit is difficult to quantify but observable. Students with documented CAD and manufacturing projects demonstrate initiative and practical capability that distinguishes applications. I've seen marginally qualified candidates secure engineering program admission based primarily on strong maker portfolios.
Let me address some frequently asked questions. What age should a child start using a 3D printer? Children as young as 8 can operate enclosed, user-friendly printers under supervision, but meaningful learning begins around age 10 to 11, when students have sufficient spatial reasoning and patience for the iterative design process. Before age 10, focus on screen-free spatial reasoning toys that build prerequisite skills. The limiting factor isn't printer operation, it's CAD proficiency, which requires abstract thinking about 3D transformations that develops during middle childhood. Do I need to buy expensive proprietary filament, or can I use any brand? Open-source printers accept any filament that matches diameter specifications. 1.75 millimeters is standard. Proprietary systems require manufacturer cartridges or chips that lock out third-party materials. The cost premium for proprietary filament is approximately 40 to 60% over commodity PLA, adding $200 to $400 to total cost of ownership over 2 years of regular use. For educational purposes, open filament compatibility offers better long-term value and enables material science exploration. How loud are 3D printers, and can they run overnight in a bedroom? Sound output varies from 45 to 65 decibels depending on design and print speed. Enclosed printers with Core XY motion operate at conversational volume levels suitable for bedroom use. Open-frame Cartesian printers generate mechanical noise from stepper motors and fans that most people find disruptive during sleep. Plan for dedicated workspace separate from sleeping areas, or limit overnight printing to quieter models. Rubber damping feet reduce vibration transmission by approximately 20 to 30%, but don't eliminate motor noise. What's the difference between cheap $200 printers and $800 models?
Price primarily buys reliability and time to first successful print. Budget printers require assembly, 2 to 4 hours, manual calibration, and troubleshooting before producing quality output. Premium models print successfully out of box with auto-calibration and quality-of-life features like automatic bed leveling, filament runout detection, and print failure recovery. Fundamental technology is identical. Both use FDM process with similar resolution capabilities. The $600 premium pays for frustration reduction, not capability expansion. For educational purposes, I prefer mid-tier options in the $350 to $500 range that balance reliability with mechanical transparency.
Can 3D printers make functional parts or just decorative objects? FDM printers produce mechanically functional parts suitable for robotics assemblies, replacement components, tooling, and structural applications. Layer adhesion creates anisotropic strength properties. Parts are stronger in X and Y directions than Z-axis, requiring design consideration for load-bearing applications. Properly printed PETG parts withstand approximately 50 megapascals tensile stress, suitable for most educational robotics and mechanical projects. Students learn to design around manufacturing constraints like wall thickness, infill density, and load orientation that directly translate to injection molding and CNC machining workflows in professional contexts. So here's the summary. The best printers for kids and teens prioritize learning value over convenience. Machines that expose mechanical principles, integrate with industry-standard software workflows, and survive the repeated failures that characterize actual skill development. Entry-level students benefit from enclosed designs that build confidence through early success. Mid-tier learners need open-source platforms that require troubleshooting and iteration. Advanced students preparing for engineering programs require capabilities that match college makerspace equipment. The educational objective isn't printing objects, it's developing the iterative design, test, debug, refine cycle that defines all engineering disciplines. A student who has independently diagnosed and corrected 20 failed prints has learned root cause analysis methodology worth more than any classroom lecture. Combined with CAD education, robotics projects, and electronics work, 3D printing becomes infrastructure for integrated STEM capability that translates directly to internship readiness and university-level project work. Budget $400 to $600 for a capable platform, $100 to $150 for essential accessories and initial filament inventory, and $30 to $50 per month for ongoing consumables. The return on that investment, measured in portfolio quality, practical troubleshooting skills, and differentiated university applications, exceeds any comparable educational expenditure I've evaluated.
That wraps up this episode of the STEM Lab podcast. Thanks for spending this time with me. New episodes come out every Monday, Wednesday, and Friday, so there's always something fresh coming your way. If this was useful, I'd really value it if you leave a 5-star rating and write a quick review. It genuinely matters because that's how other parents and educators actually find the show when they're searching for legitimate STEM education resources. And go ahead and subscribe or follow so you get notified the second a new episode drops. See you in the next one.